Jupiter is huge. Its size dwarfs everything we know in the solar system. Let's see just how big it really is. The first number that catches the eye is the equatorial diameter, about 142,984 kilometers. That stretches across more than 11 Earth diameters placed side by side. I can almost feel the stretch, like a rubber band pulled taut between two distant points. At the poles, the planet is not as wide. It flattens by roughly 6%. The polar diameter drops to around 133,708 kilometers. The shape reminds me of a spinning orange, slightly squashed by its own rotation. If I fill a sphere with water and then try to pour Earth's volume inside, the water would spill over many times before reaching Jupiter's limits. Jupiter's total volume is 1321 times that of Earth. In other words, more than 1,000 Earths could sit inside, each one a tiny marble in a massive bowl. The mass tells a different story. Jupiter weighs about 1.898 times 1027 kilograms, roughly 318 times Earth's mass. Yet the planet is mostly hydrogen and helium, so its average density is only 1.33 grams per cubic centimeter. That is a little higher than water, but far lower than rock. I find it hard to picture a world that feels almost weightless despite holding so much material. Because density is low, the outer layers are thick and fluid, extending deep into the interior. Pressure rises slowly at first, then climbs dramatically toward the core. The pressure at the center is estimated to be over 40 million atmospheres, enough to crush ordinary metal into a liquid. The notion of standing on such a surface feels absurd. We don't really know what a ground would feel like there. When we compare Jupiter to the Sun, the contrast is striking. The Sun's diameter is about 1,391,000 kilometers, roughly 10 times Jupiter's. Yet the Sun's mass outweighs Jupiter by a factor of 1,000. Visually, a telescope shows Jupiter as a bright disk, a tiny pinprick next to the Sun's blazing disk. The Sun's glare makes Jupiter seem like a distant candle, even though the planet itself is massive enough to contain many suns if we could compress them. The planet's rapid spin, about 10 hours for a full rotation, adds to its flattening. The equator bulges outward, the poles pull inward. This centrifugal force is measurable. It changes the gravity felt at the equator by a few percent compared to the poles. I sometimes imagine the sensation of standing on the equator, the ground pulling slightly less, as if the planet itself were trying to fling you outward. The sheer size also influences the magnetic field. Jupiter's magnetic envelope stretches millions of kilometers into space, forming a magnetosphere larger than the Sun's own. It sweeps up charged particles, creating auroras that glow at the poles. While this is a topic for another chapter, the fact that the magnetic field scales with size is a reminder of how dimension shapes everything else. Even the cloud bands that stripe the planet are a product of its scale. The bands are hundreds of kilometers thick, each moving at different speeds. The Great Red Spot, a storm larger than Earth, has persisted for centuries. Its longevity hints at the energy stored in a massive atmosphere, a reservoir that would be impossible on a smaller world. If I take a ruler and lay it along Jupiter's equator, each centimeter would represent about 1430 kilometers. That conversion makes the planet feel almost abstract, like a map drawn in exaggerated proportions. I don't quite understand how such a scale translates to everyday experience, but the numbers force the imagination to stretch. The volume comparison also offers a concrete image. Imagine stacking Earths inside a transparent sphere the size of Jupiter. The Earths would fill the interior, leaving only a thin shell of gas at the outer edge. The shell would be thick enough to support a mountain range of hydrogen, yet invisible to the eye. One more detail that catches my attention is the relationship between mass and gravity at the cloud tops. Surface gravity on Jupiter is about 2.5 times Earth's. A person weighing 70 kilograms on Earth would feel roughly 175 kilograms there. The increase is modest compared to the mass increase because the planet's radius is so large. It's a subtle reminder that size does not linearly dictate weight. The polar flattening also means the distance from the center to the surface varies. At the equator, you are farther from the core than at the poles. This tiny difference changes the escape velocity by a few kilometers per second. I find it hard to picture a spacecraft adjusting its launch angle just to account for that shift, yet engineers must consider it. Finally, the sheer number of Earths that could fit inside Jupiter, over 1,000, makes the planet feel almost like a container. If we could somehow hollow it out, the empty space would be vast, a cavernous void waiting to be filled. The idea of such a hollow sphere is absurd, but the math is undeniable. A single observation stays with me. The equatorial bulge adds roughly 4,600 kilometers to the planet's width, a distance comparable to the span between New York and Los Angeles. That extra stretch is a quiet testament to how rotation reshapes a world of gas. The notion of stuffing Earths into Jupiter feels like a laboratory joke that somehow turned serious. I sit with the numbers, trying to keep the abstraction from drifting into fantasy. The first step is to treat both worlds as perfect spheres, ignoring the bulge at Jupiter's equator and the mountains on Earth. Jupiter's mean radius measures about 69,911 kilometers. Earth sits near 6,371 kilometers. Dividing the two gives roughly 10.97. Raising that ratio to the third power yields the volume factor, because volume scales with the cube of radius. The result lands close to 1320. Rounding down, we say about 1,300 Earths could fill the space inside Jupiter. That number, however, rests on an idealized picture. It assumes every cubic kilometer of Jupiter's interior is available, that the planet is a solid ball of empty space waiting to be occupied. In reality, the giant is a swirling mass of hydrogen and helium, compressed to pressures we can barely imagine. Its average density is only 1.33 grams per cubic centimeter, compared with Earth's 5.51 grams. Mass and volume are therefore very different beasts. If we imagine Earth-sized marbles packed inside a larger sphere, geometry tells us the best possible arrangement fills about 74% of the container. That is the classic face-centered cubic or hexagonal close packing. Randomly tossed spheres settle at roughly 64% efficiency. The remaining gaps are empty, no matter how hard we push. So even if we could somehow freeze Earth's crust into solid spheres, the count would drop from 1,300 to somewhere between 830 and 960, depending on how neatly they settle. I find it hard to picture 1,000 solid worlds jammed together, each with its own gravity, each resisting compression. The mental image blurs, the numbers feel detached from any tactile sense. Yet the exercise does something useful. It translates a gigantic volume into a count we can grasp, a handful of familiar objects rather than a raw cubic kilometer figure. The comparison also highlights a common misconception. Many assume that because Jupiter can hold 1,300 Earths, it must also be 1,300 times more massive. That is not the case. Jupiter's mass is about 318 Earth masses. The discrepancy tells us the giant is mostly empty space, a thick envelope of gas that yields under its own weight. The density contrast is the real story, not the volume alone. When we speak of packing Earths, we also ignore the fact that Jupiter is not a rigid container. Its interior is stratified, with a metallic hydrogen layer, a molecular hydrogen envelope, and perhaps a rocky core. Each layer responds differently to pressure. If we tried to insert solid spheres, the surrounding fluid would flow around them, altering the pressure profile. The thought experiment, then, is a static snapshot, while the planet is a dynamic system. The figure remains a handy analogy for educators and communicators. Saying Jupiter could hold about 1,300 Earths instantly conveys that the planet is not merely larger. It is orders of magnitude larger in sheer space. The image sticks in the mind more readily than a statement about kilometers or cubic kilometers. That is why the number persists in textbooks and popular articles, despite its simplifications. Nevertheless, the analogy has clear limits. It does not tell us anything about the composition of the gas giant, nor about the forces at play inside it. It also sidesteps the fact that Jupiter's shape deviates from a perfect sphere by about 7% at the equator, due to its rapid 10-hour rotation. That flattening reduces the actual volume by a few percent, nudging the Earth count slightly downward. Another subtle point is that the Earths we imagine are rigid, unchanging spheres. Real planets deform under external pressure. An Earth placed inside Jupiter would be crushed, its iron core melting, its crust liquefying. The mass of the inserted Earths would add to Jupiter's own gravity, altering the equilibrium. The simple count, therefore, ignores a cascade of physical feedbacks. In the lab note spirit, I write the calculation as a series of steps, each with its own uncertainty. Radius ratio: 10.97 plus or minus 0.03. Cube of ratio: 1320 plus or minus 80. Ideal packing factor: 0.74 plus or minus 0.02. Resulting Earth equivalent count: 970 plus or minus 120. The spread reminds us that even a straightforward arithmetic exercise carries hidden error bars. It is tempting to push the analogy further, to ask how many moons could fit, or how many human-made satellites. Those questions quickly leave the scope of this chapter, slipping into topics better left for later. Here we stay with the Earth count, the most immediate way to visualize Jupiter's enormity. One practical outcome of the exercise is a better appreciation for the scale of the Jovian magnetosphere. The region where Jupiter's magnetic field dominates stretches out to several million kilometers, dwarfing the planet itself. If the planet's volume can host 1,000 Earths, the surrounding magnetic bubble can enclose a volume millions of times larger, a reminder that size is only one facet of a planet's influence. The thought experiment also serves as a caution against conflating big with heavy. In everyday language, we often use size as a proxy for weight, but Jupiter proves the two can diverge dramatically. Its bulk is mostly light gases, while Earth's compact rock and metal make it comparatively dense. The 1,300 Earth figure therefore tells us more about space than about mass. Finally, I note a concrete detail that often slips past casual observers. The outermost visible cloud layer sits roughly 30,000 kilometers above the pressure level where hydrogen becomes metallic. That distance alone is about 5 Earth radii, a thin veneer in the context of the whole planet, yet it defines the bright bands we see through a telescope. The outer skin of Jupiter is a riot of colored bands, each one a slice of the atmosphere where winds shear past one another. Those bands are not merely decorative, they mark distinct cloud decks of ammonia ice, ammonium hydrosulfide, and water. I find it hard to picture how a planet can keep such layers separated when the pressure below is already crushing. Below the visible clouds, the pressure climbs by a factor of 10 for every few hundred kilometers. Temperature follows, rising from a few hundred Kelvin at the top to several thousand deeper down. The gradient is smooth, yet the chemistry changes abruptly where a new phase becomes stable. At roughly 1 bar pressure, the familiar gases behave like a thin gas. By the time we reach 10 bars, the mixture thickens into a soupy fluid that can support waves. The fluid still carries the same composition, but its density is now comparable to that of water on Earth. That transition is what lets Jupiter hold so much mass without a solid surface. A few thousand kilometers beneath the clouds, hydrogen ceases to be a simple molecule. The immense pressure forces the electrons out of their atomic orbits, allowing them to move freely among the protons. This creates liquid metallic hydrogen, a conductive, opaque sea that behaves like a metal under earthly conditions. The term metallic feels almost misplaced for a substance that is still mostly hydrogen, but the electrical properties are unmistakable. The metallic layer is not uniform. As depth increases, the density rises, and the fluid becomes more like a dense alloy than a gas. The transition is gradual, but models suggest a clear boundary where the fluid's conductivity spikes. It is this conductive ocean that powers Jupiter's magnetic field, generating currents that swirl with the planet's rapid rotation. Jupiter spins once every 10 hours, a speed that would shred a solid body. The metallic hydrogen, however, can endure the shear because it is a fluid. The combination of rapid rotation and high electrical conductivity creates a dynamo, much like the one in Earth's core but on a vastly larger scale. The resulting magnetic field stretches far into space, forming a magnetosphere that dwarfs the planet itself. Beneath the metallic sea, many scientists suspect a dense core of rock and ice. Direct observation is impossible. We rely on gravitational measurements from spacecraft flybys. Those measurements hint at a compact region that accounts for a few percent of Jupiter's total mass. The core's exact composition remains uncertain. Some models favor a mixture of silicates, others a slurry of ice and metal. The core, if it exists, is under pressures exceeding several million bars and temperatures hotter than the surface of the Sun. Under such conditions, familiar minerals would melt into exotic supercritical fluids. We don't really know how those materials behave at those extremes, and laboratory experiments can only approximate the conditions. Even if the core is solid, it would be surrounded by a thick mantle of metallic hydrogen, then a layer of molecular hydrogen, and finally the visible cloud decks. Each layer contributes to the planet's overall volume in a way that a rocky world cannot match. A rocky planet's interior is dominated by a solid mantle, limiting how much it can expand under pressure. Jupiter's interior, by contrast, can compress and still retain a huge radius because fluids give way more easily. The pressure at the center of Jupiter is estimated to be around 70 million atmospheres. At that point, matter is squeezed into a state that defies everyday intuition. The distinction between solid and liquid blurs, and the concept of volume becomes a mathematical construct rather than a tangible space. It is a reminder that the planet's size is a product of both its mass and the unusual compressibility of its interior. Temperature also plays a role. The heat that Jupiter radiates into space exceeds the sunlight it receives, indicating an internal energy source. Part of that heat comes from the slow contraction of the planet, a Kelvin-Helmholtz mechanism that converts gravitational potential into thermal energy. The ongoing contraction subtly reshapes the pressure profile, nudging the layers inward over billions of years. The magnetic field we observe today is a snapshot of a dynamic system. Small changes in the flow of metallic hydrogen can alter the field's geometry. Spacecraft have recorded fluctuations that suggest the dynamo is not a static engine but a restless, turbulent sea. It is a reminder that even a planet of this size can be internally volatile. When we compare Jupiter to a rocky planet like Earth, the contrast is stark. Earth's interior is layered with a solid inner core, a liquid outer core, a viscous mantle, and a brittle crust. Each layer is defined by a change in phase that is largely dictated by pressure alone. Jupiter's layers, however, are defined by a combination of pressure, temperature, and composition, producing a fluid hierarchy that can shift with subtle changes. The layered structure also explains why Jupiter does not have a sharp surface. The transition from the outermost clouds to the deep interior is a continuum, a gradual blending of phases rather than a hard edge. That is why a spacecraft can descend through increasingly dense gases without ever encountering a solid ground. In the end, the planet's enormity is not just a matter of mass, but of how that mass is arranged. The combination of a thick envelope of hydrogen and helium, a metallic ocean, and a possibly solid core creates a volume that can hold more than 1,000 Earths. The same ingredients, arranged differently, would produce a far smaller world. A faint glow at the 1 megabar level persists in the data, hinting at a subtle change in the metallic hydrogen's opacity, a tiny clue that the interior still holds surprises. I start each entry with a note on pressure, because it is the most immediate thing a probe feels when it approaches Jupiter. The atmosphere is already several hundred times denser than Earth's at the altitude where the clouds turn from white to amber. That same pressure squeezes the jet streams into thin, razor-sharp bands that circle the planet every few hours. The bands are not just visual tricks, they are real wind corridors, some moving eastward, others westward, separated by narrow shear zones. In a single latitude, you can find a wind speed that rivals a commercial jet, then a few degrees away the flow reverses. I have watched the data scroll past, and the numbers jump from plus 150 ms to 150 ms in a matter of minutes of latitude. It feels like the planet is constantly trying to balance itself, a restless equilibrium that never settles. Within those shear zones sit the vortices that have earned the planet its reputation for turbulence. The most famous, the Great Red Spot, has persisted for at least 3 centuries, perhaps longer. Its size is comparable to Earth, yet its depth reaches several tens of kilometers below the visible cloud tops. I find it hard to picture a storm that can survive the loss of energy that would dissipate a hurricane on Earth in a day. The spot's reddish hue suggests chemicals being churned up from deeper layers, but the exact composition remains a puzzle. Spectral readings give us hints, perhaps phosphine or complex organics, but we do not really know. Even as the spot dominates the eye, smaller vortices pepper the atmosphere, some lasting weeks, others only days. They appear as dark ovals or bright patches, rotating either with or against the surrounding jets. Their birth often follows a disturbance in a shear zone, as if the flow momentarily tears itself and a pocket of air is set spinning. I have cataloged dozens of these, noting that they tend to migrate toward the equator before fading. Their fleeting nature reminds me that the planet's dynamics are not a static picture but a continuous experiment. The jet streams themselves are layered. Infrared observations reveal a deeper, slower wind system that runs beneath the visible bands. The upper jets are fed by solar heating on the day side, but the deeper winds seem to be powered by internal heat. Jupiter radiates more energy than it receives from the sun. I do not fully understand how the heat is transferred upward without destroying the jet structure. The models I run produce a reasonable match, yet they require fine-tuning that feels more like guesswork than physics. Beyond the visible atmosphere, a faint ring system skirts the planet. It is not the spectacular rings of Saturn. It is a narrow, dusty veil that extends only a few thousand kilometers from the cloud tops. The rings are composed mainly of micrometer-scale particles, likely knocked loose from small inner moons by meteoroid impacts. Their composition is a mixture of silicates and ices, giving them a muted gray tone in reflected light. When the spacecraft's dust detector passed through, it recorded a gentle hiss of impacts, each grain striking at several kilometers per second. The ring's brightness varies with the angle of sunlight, sometimes disappearing into the glare of the planet's own glow. 4 large moons orbit the planet in a tight, resonant dance. Io, Europa, Ganymede, and Callisto, collectively the Galilean moons, exert tidal forces that shape both themselves and the planet. Io's volcanic activity, the most intense in the solar system, is driven by the constant flexing of its interior as Jupiter's gravity pulls it along its elliptical path. The eruptions spew sulfur and ash into space, some of which becomes part of the faint ring. Europa's subsurface ocean is kept liquid by the same tidal heating, a process that also cracks its icy crust, creating linear features that we can see from afar. Ganymede carries its own magnetic field, a tiny bubble that interacts with Jupiter's massive magnetosphere, while Callisto, the most distant, retains a heavily cratered surface that records the history of impacts over billions of years. The magnetosphere itself is a gigantic, rotating shield, extending millions of kilometers into space. Charged particles trapped in its stream along magnetic field lines toward the poles, where they precipitate into the upper atmosphere, creating auroral ovals that pulse with ultraviolet light. The moons act as conductors and obstacles within this flow. Io, for example, drags a plasma torus, a donut-shaped ribbon of ionized material, around the planet. This torus feeds the magnetosphere with fresh particles, altering its density and temperature. When the spacecraft crossed the torus, its instruments recorded a sudden rise in electron flux, a reminder that the moon is not a passive satellite but an active participant in the planetary environment. The interaction between the moons and the magnetic field also generates electric currents that travel along the magnetic lines, connecting each moon to the planet's ionosphere. These currents can induce heating in the moon's interiors, a subtle contribution to the tidal heating already mentioned. I have run a simple calculation that suggests the current induced heating on Europa could be a few percent of the total energy budget, enough to matter, perhaps, for the maintenance of a subsurface ocean. All these motions, jets, vortices, rings, moons, magnetic currents, are linked by the planet's rapid rotation. Jupiter spins once every 10 hours, a rate that flattens its shape into an oblate spheroid. The equatorial bulge is about 20% larger than the polar radius, a physical reminder that centrifugal force is a dominant player. The same spin also organizes the jet streams into a pattern that repeats roughly every 30 degrees of latitude. I sometimes wonder whether the planet's rotation is the master conductor, or merely a background beat that the other processes follow. I have tried to capture the sense of constant motion with a few measurements, but numbers alone cannot convey the feeling of standing on a spacecraft and watching a band of ammonia clouds drift past, their edges tinged with a faint green. The view is both serene and unsettling, as if the planet is breathing slowly while its interior roars. The contrast between the quiet appearance of the rings and the violent eruptions on Io underscores how diverse the system truly is. When I look at the data from the magnetometer, I notice a tiny, recurring spike in the magnetic field strength as the spacecraft passes over a specific longitude. The spike aligns with a known bright spot in the aurora, suggesting a localized enhancement of particle precipitation. It is a small detail, but it hints at a coupling between atmospheric dynamics and magnetic processes that we have not yet mapped fully. The first time a probe slipped past Jupiter's cloud tops, the radio hiss in the data streams sounded like a distant, low-frequency drum. I still hear that tone in my mind when I think about how thin our curiosity feels against a planet that could swallow 1,000 Earths. Voyager 1 and 2 arrived in 1979, each taking a brief, high-speed glance at the giant's bands. Their instruments recorded the speed of the winds, hundreds of meters per second, and the sudden flicker of lightning that crackles a few hundred kilometers above the visible layers. The images were grainy, but they gave us a first sense of the scale, a reminder that the planet's bulk is not just a surface but a deep, roiling mass. Galileo entered orbit in 1995 and lingered for 8 years. It dropped a probe into the atmosphere, a small capsule that survived only minutes before the pressure crushed it. Still, those minutes yielded temperature and pressure readings that still sit in my notebook, numbers that feel too high for a world made mostly of hydrogen and helium. I find it hard to picture a place where the pressure is 1,000 times that at sea level, yet the gas does not solidify. Juno arrived in 2016, slipping into a polar orbit that lets it skim just above the cloud line. Its microwave radiometer peers down through the storms, mapping the distribution of water and ammonia. The data suggests the planet's core may be less compact than we once thought, perhaps a fuzzy region of metallic hydrogen rather than a solid iron ball. We don't really know whether the core is a distinct object or a gradual transition. The Juno team has also traced the magnetic field with unprecedented detail. The field is tilted and offset, producing auroras that pulse like a distant lighthouse. Those auroras illuminate the upper atmosphere in ultraviolet, a faint glow that our eyes would never catch. Watching the auroral curtains shift, I am reminded that even a planet so massive can have subtle, almost shy variations. Upcoming missions promise to tighten the picture. Europa Clipper, slated for launch next year, will fly past Jupiter's icy moon dozens of times before finally diving close to the moon's surface. Its instruments will listen for magnetic signatures that hint at a salty ocean beneath Europa's crust. While the focus is the moon, each flyby will also sweep past Jupiter's magnetosphere, adding fresh data about the planet's outer layers. JUICE, Jupiter Icy Moons Explorer, will take a different path, lingering in the system for 3 years. It will orbit first around Ganymede, then Europa, then Callisto, while continuously measuring the plasma environment. Those measurements will feed back into models of how Jupiter's rapid rotation drives charged particles around the planet. The mission will also carry a microwave radiometer similar to Juno's, but tuned to probe deeper into the atmosphere. Both missions illustrate a growing trend in planetary science. We are no longer content with a single snapshot. We now collect time series, watching how storms evolve over months, how the magnetic field shifts, how the radio emissions wax and wane. The data sets are massive, and the analysis feels like trying to hear a single instrument in an orchestra that never stops. Comparing Jupiter to the gas giants, we find orbiting other stars adds another layer. Many exoplanets are called hot Jupiters because they sit close to their suns, their atmospheres blistered by stellar heat. Jupiter, by contrast, sits far enough out that its atmosphere stays relatively cool. Yet the underlying physics, core accretion, rapid rotation, deep convection, appears to be shared. In that sense, Jupiter serves as a laboratory for interpreting distant worlds we can only see as dim points of light. One open question that keeps resurfacing is the exact composition of the deep interior. Laboratory experiments can compress hydrogen to a few megabars, but Jupiter's core sits at pressures exceeding 40 megabars. We can model metallic hydrogen, but we lack a direct sample. The uncertainty trickles down to our theories of how the planet radiates heat. Jupiter emits more energy than it receives from the Sun, a fact known since the 1970s, yet the mechanism that transports that heat from the interior to the clouds remains hazy. Another puzzle is the persistence of the Great Red Spot. The vortex has survived for centuries, shrinking slowly but never vanishing. Some simulations suggest that deep-seated jet streams feed it, while others argue that the spot is a surface phenomenon sustained by differential heating. The Juno data show a complex pattern of winds that change with depth, but we lack a full three-dimensional map that could settle the debate. Planetary formation theories also lean on Jupiter as a benchmark. In the core accretion model, a solid core of roughly 10 Earth masses gathers gas from the surrounding nebula. Yet the recent measurements of water abundance hint at a lower than expected metallicity, which could imply that the planet formed in a region of the protoplanetary disk that was already depleted of heavy elements. If that is true, the whole timeline of how the outer planets assembled might need revision. The ongoing analysis of Juno's gravity field adds yet another piece. Small variations in the planet's gravity suggest that the interior is not perfectly uniform. There are bands of denser material aligned with the visible cloud belts. Those bands could be deep currents of metallic hydrogen, moving like slow rivers beneath the stormy surface. It is tempting to imagine a hidden ocean of liquid metal, but the data are still noisy. Even as we gather more measurements, the sheer size of Jupiter keeps putting our instruments in perspective. A single Juno pass over the North Pole lasts only a few minutes, yet during that time the spacecraft records thousands of data points. Those points, when plotted, form a thin line that traces the magnetic field's subtle twist. The line is almost invisible against the background of the planet's bulk, a reminder that the details we chase are often a whisper in a thunderstorm. The comparative work with exoplanets also forces us to confront the limits of what we can infer. When we see a distant gas giant transit its star, we measure its radius and mass, perhaps a hint of atmospheric composition from a spectrum. Those numbers are crude, and we must lean on Jupiter's measured properties to calibrate our models. If our Jupiter data are incomplete, the extrapolation becomes shaky. Future laboratory work may help. High-pressure physics experiments using laser-driven shock waves can briefly reach conditions similar to Jupiter's core. Those experiments produce fleeting flashes of light, and the detectors capture spectra that hint at how hydrogen behaves under extreme compression. Translating those brief moments into a planetary scale picture is a challenge that still feels a bit like trying to read a novel from a single word. The human element in all of this is easy to overlook. The engineers who designed Juno's solar panels had to account for the weak sunlight at 5 astronomical units, a problem that forced them to use a larger array than any previous mission. The mission planners who plotted the polar orbit had to accept that the spacecraft would endure radiation doses that would have killed earlier probes. Those choices reflect a willingness to accept risk in order to glimpse the hidden layers of a planet that dominates our sky. Even the names we give to features betray our perspective. The Great Red Spot is a label we assign to a storm that has outlasted human records. Its color shifts, sometimes turning more orange, sometimes fading to a dull brown. The variability reminds me that the planet is not a static monument but a living system, constantly reshaping itself. There are still questions that seem to sit just beyond reach. Does Jupiter have a solid inner core at all, or is it a gradual transition from metallic hydrogen to a denser mixture? How deep do the jet streams extend? Do they reach the core, or are they confined to the outer envelope? What role does the planet's rapid rotation play in shaping the magnetic field's odd geometry? Each of those questions can be answered only with a combination of deeper measurements and refined models. The upcoming Europa Clipper and JUICE missions will not solve every mystery, but they will add new layers of data that can be cross-checked with Juno's findings. The hope is that, over the next decade, the mosaic of observations will become dense enough to reveal patterns we cannot yet see. Until then, the picture remains incomplete, a sketch that we keep filling in line by line. One small detail that keeps surfacing in the raw data is the faint, steady hiss of decametric radio waves that drift past Juno's antenna as it passes over the North Pole. The hiss is barely above the instrument's noise floor, yet it persists, a subtle reminder that the planet's magnetosphere is alive with low-frequency chatter.